Okay, so my talk is basically what I put up there, I guess. So I'm going to be talking about data that was taken with the Sloan Digital Sky Survey telescope. You may know that the first data release of BOSS survey was actually sometime last week, some of you. And so all the data that's been used is actually now public. So I encourage you to do similar things if you want with the data. So I'm going to talk about Lyman alpha emission from redshift of 2 to 3 galaxies. And those of you who know about Sloan and BOSS should know that, of course, it's not targeted to look at galaxies in that redshift range. So I'm going to just having a bit of fun with the data to try and get some signal out of it. And you'll see that whether it works or not. It works a little bit, so you'll see. OK, so I'd like to thank the other people in the BOSS Lyman Alpha Forest and Quasar working groups. So all these people here. Mostly I was talking to Jordi Maralda about this, and he's the one also involved, most involved. And if my voice goes, then I'll pick one of you at random to continue the talk, if that's okay. All right, so a little plan. I'll just talk very briefly about Lyman alpha emission in the high redshift universe. So there are two sources of Lyman alpha emission that I'll be most interested in. Basically Lyman alpha emitters, as they're called, so Lyman alpha emitting galaxies, and also Lyman alpha emission from the IGM, which has never been seen, and I'll be able to put maybe some constraints on that as well. And so then the middle part will be to talk about how we can actually use spectra of redshift of, say, 0.5 to 1 galaxies from BOSS to measure Lyman alpha emission from redshift 2 to 3 galaxies. And the motivation for trying to do this is that Sloan Data Release 9, for example, has around, say, 600,000 fiber spectra, and it would be nice to be able to use them to do something, okay, apart from their stated science. And so we can actually tease out some signal from that, and I'll give you some results and conclusions. Okay, so traditionally, many surveys have been done to look for Lyman alpha emitting galaxies. Here's one from Subaru, SuprimeCam. This is one of the largest efforts, and basically most traditional efforts use narrowband imaging. And so here's some nice large field, and these are all pretty bright Lyman alpha emitting galaxies, and you can trace out structure, and you can look in this narrowband map, and you can pick out sources. I'm in an aperture, and you can look at their flux, for example, and you can make things like the luminosity function. So that was a redshift of 3, which is what I'm interested in here. Here's another version. This is done with a prototype of the integral field unit that's going to be on the Hobby Eberly telescope, Virus. And so this is for pretty bright, again, Lyman alpha emitters. You can see the line flux limit here is 5 times 10 to the minus 17. So we're going to be using these units of ergs per second per centimeter squared. So so basically with those flux limits, you can make a relatively bright end of the luminosity function. And it's interesting to know what goes on at the fainter end. Basically what the slope is going, and whether there are lots of faint Lyman alpha emitting objects we can't see. Also, another question we like to ask is, in these surveys, you typically pick out sources that are, say, 5 sigma peaks, and then you work out the flux from them, but you could be missing some very large extended halo around them, or there could be other things emitting Lyman alpha which are fainter, which you just don't see. So we'd like to constrain those. Here's a fainter survey. This is from some Nature paper by Hayes et al. And the interesting thing they were doing here is they went fainter, but also they were comparing the star formation rate that you get from H alpha, which is not sensitive to dust in this context, with what you get from Lyman alpha, where they've converted the H alpha into the Lyman alpha luminosity. And you can see that from H alpha, the comparison between H alpha and Lyman alpha tells you basically what the escape fraction of Lyman alpha radiation from galaxies is. And so Lyman alpha radiation bounces around a lot. It scatters a lot inside the galaxy. Then it ends up getting absorbed. Apparently, 95% of it ends up getting absorbed by dust inside the galaxy. Apparently, at least, it's when you compare that from the H alpha, that's what you see. The escape fraction is apparently about only 5%. Okay, so one question you might want to ask is, actually, although we see this 5% when we're looking at these Lyman alpha emitters, maybe some of that actually scatters out of the galaxy, isn't immediately absorbed by dust, and actually scatters out into the medium around the galaxy, and you might be able to recover that as some sort of faint Lyman alpha emission around the galaxy somehow, sort of more distributed. And so we can try and constrain that as well. So here's just another plot from that paper, a related one, showing how the escape fraction declines at low redshift, measured in the same way. So basically at redshift 0, we've got a tiny escape fraction of Lyman alpha emitters, and at high redshift, it's almost all of it escapes. And so obviously that's just to do with the amount of dust that's being produced in the universe. So okay, those are Lyman alpha emitting galaxies. What about the other thing? Well, Lyman alpha emission from the IGM has been some sort of holy grail of people working on the IGM. The idea would be to actually see, you basically get the Lyman alpha forest, which is the absorption and Lyman alpha systems, but of course that Lyman alpha radiation has to be re-emitted again, and the question is, how can we detect it? It's very, very faint. Here's some paper from nearly 20 years ago now, of Gordon Weinberg, and they said, okay, we could try and look for this. The mean Lyman alpha surface brightness is about 10 to the minus 22 ergs per second per centimeter squared per arc second. So compare that to the line flux of the objects of 10 to the minus 17 or so in the surveys I was showing you, and obviously they're a long way from being able to detect this. Okay, so questions that I'll try and answer at least a bit during this talk, things we might want to answer. Number one, what is the mean Lyman alpha emissivity in the universe, and how does that compare to what we get if we actually integrate the luminosity function of known Lyman alpha emitting galaxies and just see, what is the difference between the two? This could tell us about fainter galaxies or other sources. Related to this, number two, the escape fraction of Lyman alpha from galaxies at 2.5, the pieces that can be seen directly, is about 5%. So how much of that is absorbed by dust, and how much of it actually scatters out further out into the intergalactic medium around the galaxy, and we can try and detect that. And then number three, can we actually detect this sort of holy grail piece, the IGM fluorescent Lyman alpha emission? So that's more difficult. Okay, so people have attempted to tackle these kind of issues before with very ambitious observations. So here's one, Bunker et al. Actually it ended up being published as Rauch et al. Here's an AAS abstract. I want to show you, over several years we've accumulated 150 hours integration on a single field with 8 to 10 meter telescopes. Okay, now that's not ambitious, I don't know what is, okay? So that includes VLT, Gemini, and Keck, okay, all on a single field, looking for Lyman alpha emission, okay? And you can see the sensitivity here, okay, it's not 40 orders of magnitude worse than the other one. There should be a minus sign there. Okay, okay, it's 10 to the minus 19 ergs per second in a line per centimeter squared. Okay, so remember I told you usually people look at the order of 10 to the minus 18, 10 to the minus 17. These guys look at 10 to the minus 19. I told you that from the IGM, the fluorescent emission, we expect 10 to the minus 22, okay, surface brightness. So we're still not there, okay, and so they do detect some faint Lyman alpha emitting galaxies. So what we'd like to do is, that was on 8 to 10 meter telescopes, 150 hours. Instead, we'd like to use a venerable 2.5 meter telescope and try and do better than that. Okay, so the advantage we have is that we have lots and lots and lots of fibers to play around with, and so we'd like to use all of them, and if we can, to actually look for Lyman alpha emission. Okay, so that's what we'll do. So here's the Boss spectrograph. There's 1,000 fibers there. Let's try and use that. Okay, when we're looking for Lyman alpha emission, okay, we're obviously looking for this transition. In the IGM part, it makes sense to look for places where there was lots and lots of absorption, lots of photons coming in, being absorbed, and then re-emitted. Where's the place where there are the most of those? Basically, it's around quasars, okay, that most of the photons are being pumped into the intergalactic medium. So we'll look for Lyman alpha emission in fibers that pass close by quasars. So imagine a quasar here. We've got some sight lines going past it which have pixels in there, the spectra, okay? And what we'd like to do is look, can we see excess Lyman alpha emission close to the quasar that tails off into the mean background as we move further away? And so what we'd like to do is we'd like to have many, many blank sky fibers to do this. Unfortunately, Sloan was doing baryon oscillations, okay, which may or may not be interesting, but it used a lot of fibers, and so unfortunately, we don't have many sky fibers, but we do have tons and tons of galaxy fibers. So what we do is we'll just use galaxy fibers, and we'll subtract off the model galaxy. Okay, so basically the model galaxies are basically the galaxies observed by Sloan. They're these absorption line, just elliptical galaxies, very well studied. We just subtract off the model galaxy, and then as a result, we've got some sort of residual spectrum, and if there's any sort of sharp Lyman alpha emission features in that, we'll pick that up as an excess around the quasar. Okay. Right, so we expect two contributions to this Lyman alpha emission around quasars. The first one is this fluorescent emission. Close to quasars, mainly reprocessed quasar radiation. Okay, so if that red star is the quasar, we expect the filaments of gas around it to be sort of lit up and fluoresce. And then the main contribution, the main known contribution is emission from star-forming galaxies, which will be clustered with the quasar. Okay, and they could even be faint galaxies. And these things, well, obviously there'll be a galaxy-quasar cross-correlation function, and so they'll be clustered around it. And so we'll get an excess around these massive halos that are the quasars. Right? So we can use both of these things to help us look for this Lyman alpha emission. Okay, so here's some theoretical prediction of the fluorescent emission from Kolmai et al. So she did radiative transfer simulations in the Lyman alpha line, and you can see this is a field around, I think, a quasar in the simulation. This is a narrowband image, and this is a slit in the spectrum direction. And you can just see that the surface brightness at the top there is going from 10 to the minus 18 in very bright regions down to 10 to the minus 24 in regions where there's no gas. Okay, so it's going to be tough. I don't have any better predictions than this. I haven't. I should talk to Juno and get her to make predictions from this simulation for these observations, but we'll do some rough estimates in a second. Okay, so the predictions, well, I'll just keep it very simple as we're not expecting to see much signal. Okay, so I'll just say, let's imagine the profile of the Lyman alpha emission around quasars is equal to the mean surface brightness times some power law cross-correlation function. Okay, the cross-correlation function between Lyman alpha emitting galaxies and quasars. Okay. And so this will give us a handle on, say, the mean surface brightness if we substitute in, say, what we think the cross-correlation function is. So from measurements of quasar bias and Lyman alpha emitting bias, or faint Lyman alpha emitters, we get values for the bias of those two objects. The cross-correlation bias turns out to be about roughly 3. And so the R naught in the power law correlation function, redshift 2.5, should be about 4 megaparsecs. Okay. Then the second piece, the mean surface brightness, as a prediction, we integrate the known Lyman alpha emitter luminosity function, and we expect a mean surface brightness of about 10 to the minus 21, okay, in these ergs per second per centimeter squared and per angstrom. Okay. So the prediction for fluorescent AGN emission, okay, I showed you the radiative transfer simulation. That was very clumpy. It's difficult to see what the mean would be if you average around a quasar. So a very rough calculation, let's say, supposing we had a quasar which had 10 to the 44 ergs per second in the Lyman alpha line, we say, supposing that all scatters out all the way to our R naught of 4 megaparsecs, what would the emissivity be due to that? And it would turn out to be this, 5 times 10 to the 39 ergs per second per prober megaparsec. And that comes out to a surface brightness, once you redshift it, to about 10 to the minus 21. Okay? And so it's of a similar surface brightness to the Lyman alpha emitters. Okay? And so we should use real predictions from Lyman alpha radiative transfer, but for now it's about of that order. Okay, so now we come to doing the observations. Are there any problems we should worry about? Well, one of them is that we have all these fibers packed close together. They end up getting dispersed and onto some CCDs where they're all very close together, of course. We like to pack them in there. And it turns out that light actually leaks from one spectrum to the next, just because we have some profile here, and the aperture that we extract the spectrum along, say this is spectrum 1 and spectrum 2, ends up taking a bit of the nearby spectra into it. Okay? And so we actually have to worry about that. You can imagine that if the nearby spectrum here was actually, say, the quasar spectrum itself, then obviously that would have strong Lyman alpha emission at that redshift, and we would end up picking that up, thinking it was due to the medium around the quasar. So we have to be very careful. So here's what we do. This is a huge mess, but you shouldn't worry about this is all noise, but what I'm plotting here is the distance between quasar and galaxy, and here's the delta fiber number, okay? So delta fiber number of 0 is the same fiber we're not plotting, but plus or minus delta fiber number of 1 is basically when there's a fiber next to this fiber, okay? And so when there's a fiber next to it, we end up getting, even at very large distance, we end up getting a strong signal. Okay, and this is obviously spurious, okay, because the quasar and pixel are very widely separated, but in fact on the CCD they're just next to each other. Therefore, we end up getting this spurious signal. So what we end up doing is, I just end up cutting out plus minus 5 fibers. That's pretty conservative, and changing that doesn't really change the results. If you go down to plus minus 1, then you start getting contamination. So the solution is do not use quasar and galaxy spectra within 5 fibers. Okay, so now let's have a look at what the actual result is. So remember, it's just, it doesn't look very impressive, but it's actually, as we'll see, significantly better in terms of the limit than what you get with 150 hours of 10-meter telescope time. So, it's still worth looking. Here's the surface brightness here in units of 10 to the minus 20, and then here's the distance between the pixel and the quasar. Okay, and so close to the quasar, we expect to see some excess emission, Lyman alpha emission from galaxies, say around quasars, or maybe fluorescent Lyman alpha emission, then it tails off. And so there is, a non-zero signal there. It's not great. That blue line is just a power law fit that I just did a power law fit. And so I broke this up because, we have more than 500,000 spectra. It's easy to break it up into lots of subsamples to make a covariance matrix. So I did that with jackknife and did a power law fit with all the covariances. And so this is what it looks like. So here is the mean surface brightness. Okay, and then this is the gamma, the slope of the power law cross-correlation function. And remember that you expect the slope of the cross-correlation function to be roughly minus 1.8 as it is, for the correlation function of, say, galaxies and so on. And so really what you could do, if you're willing to assume that and make a prior for that, you can cut across here and pick that value. It's unlikely to be down here, but strictly speaking, it is consistent with a very, very steep thing as well. So you can see here 1, 2, 3 sigma contours, and so depending on what you think about the slope, we've got, it could be, say, a 3 sigma detection, and the mean surface brightness that we get is, say, 5 times 10 to the minus 21 in these units. And here's the limit from Rakedel. It was 8 times 10 to the minus 20. So that's what they could do with 92 hours of VLT time. And so here, what about the predictions? Well, the known Lyman alpha emitting galaxies, if you integrate up the luminosity function, the pieces that are actually seen that go into the luminosity function is this blue circle. And then supposing we actually assumed that we get the Lyman alpha emission of the galaxies from H alpha, and then assuming no dust, this is a factor of 25 more, it's the green circle. And so the effect of dust is going from green to blue. And then the question is whether really all of it's absorbed by dust, or whether some of it actually scatters out into the IGM and is just not seen in those other observations. And that could move things up, right? And so, of course we only have a 3 sigma detection. You can't really discriminate very much, but you can say, okay, it's consistent with there being some possibly being scattered out further. Okay, I'm nearly done. Okay, so can we do some little checks on this, just to see that we, any other systematic. So one thing, we could randomize the galaxy 5 angular positions, and so we can do that and we get no signal, which is fine. Another thing, which is a bit of a better test, is to center on some wavelength other than Lyman alpha, and so I've done this for random wavelengths that are at least 50 angstroms away from Lyman alpha, and here's just one of them. This might be centered on, I think 200 angstroms more, so 14, 16 rest wavelength, and we don't get any excess. We don't detect any excess as consistent with a null signal. So basically, we don't find any other emission except for the Lyman alpha line, okay, which is good, as it's the strongest one. Okay, and then you can do other things. You can, okay, we have only a slight detection, but you can go crazy things like cutting up into upper and lower redshift halves to see, and that's the low redshift half, so mean redshift of about 2.2, and the upper redshift half 3.1, and they're not very different. the detection is not so good for the upper redshift, and if you had better data, you could constrain the evolution of the mean Lyman alpha intensity of the universe. Okay, so finally, the conclusions. I'll just go back to the 3 questions I said we'd like to try and answer at the beginning. So what is the mean Lyman alpha emissivity in the universe? And we have a 3 sigma detection, say, of the mean Lyman alpha emissivity, and it compares to the integration of the known luminosity function by being about 3 times more than that. Okay, so the question is, where does that extra stuff come from? And of course, we can't really tell, but we can constrain things. So, for example, we know that 5% of the Lyman alpha emission can be seen directly at redshift 2.5, and people thought previously that 95% was absorbed by dust, but because we actually can see in the mean intensity a factor of 3 more than there is in the luminosity function, then that means that maybe 15% scatters into the IGM and we're detecting it. Okay? The third one, the most ambitious one, can we detect fluorescent emission from the IGM? And we can put a limit on the excess surface brightness over known Lyman alpha galaxies of 5 times 10 to the minus 21. That's about 10 times better, a bit more than 10 times better than previous limits. And we may or may not have actually detected fluorescent Lyman alpha emission. We can't tell because of this other component, but at least we can put limits, assuming that that's an upper limit. Okay, that's it.